Today we will be talking about turbo machines. The presenters are myself, Katie Colman, Kaylee Conrad, Haley Formby, and Hope Walter. So first, what are turbo machines? They play a huge part in our daily lives, and especially as engineers, it's important we understand them. So, turbo machines are mechanical devices consisting of several blades attached to a rotor, which creates a pathway that the fluid moves through. These devices add or extract energy to a fluid through the interaction between the fluid and the device. And obviously, whether they add or extract energy is dependent on if it's a turbine or pump. Just so you know, the term pump refers to all pumping machines. So that includes pumps, fans, blowers, compressors, etc. The fluid running through these machines can be either a gas, a vapor, or a liquid. And depending on what the fluid is, creates new factors for the device. So, for example, if it is a gas, you might have to think about compressibility effect. And if it's a liquid, you might have to consider cavitation, which is the formation of vapor bubbles if the pressure is changing. Turbo machines are classified as axial flow, radial flow, or mixed flow. And some examples include window fans, propellers on ships, compressors in automobile, turbochargers, etc. So like I mentioned the energy before, this is an example of a fan. And in order to do math around this, you have to make some assumptions, which is that the fluid is moving smoothly, which is perfectly guided over the blade so that you can assume it's parallel, and that the fluid leaves and enters for the same distance from the axis. So in this example, as you can see, you have V, which is the absolute velocity equal to the relative velocity and the blade velocity enter and leaving the system.
Okay, now we're going to talk about the differences between a turbine and a pump, since both of them you can see are in different turbo machines, depending on whichever one you're looking at. So for turbines, they can extract flow energy from the fluid and cause the fluid to do work onto the rotor blades. The tangential force of the blade on the fluid and the blade motion are in the opposite directions in this case, if you're looking at it from like a force diagram. There are two types of turbines, generally speaking. There's impulse and reaction turbines. And some examples of turbo machines with turbines are aircraft gas turbine engines, steam turbines, dentist drill air turbines. Now, for pumps, they add flow energy and they do work on the fluid to move or increase the pressure. Tangential force of the blade on the fluid and blade motion are in the same direction in this case. And some examples are window fans, propellers, automobile compressors, and space shuttle fuel pumps. Now, they do have some similarities. They both operate with gases, liquids, and vapors as their fluids. Cavitation can occur when dealing with liquids for both turbines and pumps, and they can be of radial flow, mixed flow, and or axial flow. Now we have some key characteristics of the centrifugal pump, which is one of the most common radial flow turbo machines that we're going to look at. There are two main components. There's the impeller, which is made of blades called vanes, as you can see in the diagram over here. And then we also have the casing, which is this, that encircles the entire impeller. Now, the fluid is sucked in through the eye of the casing and flows radially outward, as you can see, also in this diagram, and energy is added by the blades to increase the pressure and the absolute velocity. Now, I want to make a side note. Their impellers tend to be curved, as you can see from the diagram here, and they can be curved in three different ways. The backwards kind is the most common. The forward impellers generally make flow unstable, so they're not used as often. And radial impellers are ones that are not curved. They're more straight, and they're for small, inexpensive pumps because they're generally not as good as backward impellers.
Okay. So when it comes to centrifugal pumps, we do have those key characteristics, and then we have different variations you can use with them. For casing, you can have volute-shaped casing, which reduces the velocity of the fluid leaving and thus converts kinetic energy into an increase of pressure, and it creates uniform flow. An adaptation of the volute-shaped casing is diffuser pumps, which use diffuser vanes, which are added around the impeller to decelerate flow as the fluid is directed into the casing. You also have open or closed impellers, as shown on the right, single or double suction, and double suction reduces the thrust on the shaft and reduces inlet flow velocities. And then there are single and multi-stage arrangements. A multi-stage arrangement consists of several impellers on one shaft in series, and this is used to develop a very large discharge pressure. When it comes to centrifugal pumps, there's also math involved, and some of the key takeaways are this equation for work done by the shaft and the ideal head rise. And you can see the relationship shown below. And then, as mentioned before, it was the ideal head rise, but there are considerations for real pumps, and you have to determine actual head rise, which is determined experimentally. And you also determine the power transferred to the fluid as shown to the right, the overall efficiency, which is the power gained by the fluid over the shaft power driving the pump. And this denominator is often referred to as the brake horsepower. The efficiency is diminished by hydraulic, mechanical, and volumetric losses. And then in the graph shown below, at zero discharge, this head is called the shutoff head, which is the rise in pressure head across the pump with the discharge valve closed. And power here is dissipated by heat, which will cause damage if run for an extended period. As a continuation of these considerations, you also have the net positive suction head, which characterizes the potential for cavitation, which is when the liquid essentially boils because the pressure is reduced to the liquid's vapor pressure. It's defined as shown here. And your available net positive suction head cannot exceed the required net positive suction head. Your operating point occurs where the system equation meets the pump performance curve as shown below, and the pump can be arranged in series or parallel. Series will increase both your flow rate and your head rise, and parallel will increase your flow.
One application of a turbo machine is a centrifugal heart pump. This is one of many machines of the family of ventricular assist devices available for those suffering from advanced left ventricular heart failure. This is usually a temporary solution, commonly used until appropriate donor for a heart transplant can be found. In a normally functioning anatomy, freshly oxygenated blood is delivered to the heart from the lungs by way of 4 pulmonary veins, right here, here, and over here. Right here. These 4 veins empty into the left atrium, which is a circular area right here. This is a small chamber that sits atop the left ventricle, which is right down here. Blood from the left ventricle will pass through a valve called the mitral valve and enter the left ventricle. From there, pumping action of the left ventricle will deliver blood through the aorta. This is the large vessel here, and up through its associated veins to deliver oxygen to the body tissues. In a diseased left ventricle, this pumping action is insufficient, and that leads to decreased output into the aorta. One specific type of centrifugal heart pump is an intrapericardial continuous flow centrifugal pump. This device is surgically implanted into the pericardial cavity, and that's a fluid-filled area that's located between the tough outer protective layer of the pericardium and the heart itself. Attached to this port is an inflow cannula. Here's the inflow port. The cannula is not here. The inflow port is extended through the heart muscle layer and into the ventricle itself. Attached to this port is an inflow cannula, and this is where the blood is drawn into the device from the left ventricle by action of the impeller. Blood then exits the machine at the outflow port, which is down here, right here. That is attached to an outflow cannula, right here, that delivers blood to the aorta. Percutaneous lead seen here is where, right here, is where the device is connected to external power source in the controller. You can see the external power source in the controller right here. One specific model of the intrapericardial centrifugal pump is a heartware pump manufactured by Medtronics. As seen here, at the top is the inflow port without the cannula. And at the bottom is the outflow port, also without the cannula. And the impeller is inside of a casing. The example has left out the inflow and outflow cannulas, but you can see the percutaneous lead right here that exits through the abdomen that connects to the power source in the controller. The impeller of this model is capable of speeds up to 2,000 to 3,000 revolutions per minute, allowing for a maximum output of 10 liters a minute to be delivered to the aorta. which is sufficient and pretty good, considering a properly functioning left ventricle in an adult delivers approximately 5 liters per minute. And that concludes our presentation. Thank you all for watching.